Okay, so let's remind ourselves where we were here. We did that problem. This is the last one I think we did where we had something sort of cantilevered out. Well, it's at least, I'm not in slideshow mode. I'm not in slideshow mode. That's what the problem is. All right, there we go. Let's hope that works. So we had a lamp and a beam, and you'll see problems that are sort of similar to this. And then a cable. This beam could rotate down if we just left it with the lamp hanging there, or even if the lamp weren't there, the beam would rotate down and slap the wall, but for this cable. And so one of the things we want to find out in this problem is the tension in the cable. And we also talked about how there's got to be both horizontal and vertical force components. And we found that out by doing the sum of the forces, x components of forces, where I chose x to be horizontal, is 0. Sum of the force y components equal to 0. And the sum of the torque components. Again, since nothing's really rotating, I don't have to choose this as my axis of rotation where it's hinged right there. It's tempting because it actually is a hinge, but you don't have to. And in fact, I could have summed torques about this point over here. Maybe that could be my axis. Nothing's moving, so maybe it could have rotated about there. It's hard to tell because nothing's moving. There's a definite, one thing just to close the loop on this, there's a definite good reason to sum torques about this point that I'm pointing at right now. And that is because two forces are being applied at that point. And they're unknown forces that I would like to know. But unfortunately, I've got 3 unknowns. And I don't want my 3 unknowns all appearing in 3 equations, or that's going to make my life kind of a pain. Since the moment arm for both the Fx component and the Fy component is 0, right? Whenever a force vector passes through the axis of rotation, the moment arm is 0. Fx contributes 0 torque, Fy contributes 0 torque, and that means they're not going to come into the torque equation. The only thing that came in was t, so I could solve right away for t. So sometimes, if you're just thinking about strategies for problem solving and there's no obvious axis to use, you might just think, well, if a lot of my unknown forces are going through a particular location, I might choose that as my axis to sum torques about, set it equal to 0, just because those forces won't appear. And we'll see another example in the homework where that happens. In any case, we had 3 equations and 3 unknowns. Whether they're simple or complicated, it wasn't too hard to solve for them. This is the last one that was on the worksheet that we were looking at on Friday, just sort of a biologically motivated problem where someone is holding a ball of mass 5 kilograms in their hand. We're going to treat it like a point mass. We're going to imagine that the arm is being held horizontal, upper arm vertical, and the bicep has to hold it up to keep it from rotating. And the question is, how much force does the biceps have to exert to hold something like this in the hand? So just to make it's not the most realistic model, it's pretty simple, but we're going to imagine that in this case, the center of mass of the forearm itself, this whole forearm has some mass, right? We can think of it as a bar that's not necessarily a uniform beam, but we're told the center of mass is here, 15 centimeters from the elbow joint. And the 5 kilogram ball that's being held is 35 centimeters out from the elbow joint. And the biceps muscle, of course, can't be pulling right at the elbow joint. It's got to be attached a little bit outward to actually exert a force. It's 5 centimeters in this model away from the elbow joint. And the question is, well, find the force the biceps muscle has to exert on the arm. And then there's another force here on the forearm, and that is the elbow is pushing down on the forearm at the elbow. You can kind of imagine if it weren't pushing down there, everything would rotate around the biceps muscle. This would rotate down. It would rotate up where the elbow is. And, so there's got to be a downward force there to hold it. And the second part is find that downward force that the elbow. It's kind of hard to see stuff in the diagram, but there are 4 forces labeled, right? The FM is the muscle force. I guess that's what the M is. I can't even see this subscript there. And I can't really see what that is. C, I don't know. Well, what is that subscript? But in any case, that's supposed to be the forearm mass, and it's located at the center of mass. Okay, so I'm just going to, as always, choose some conventions for axis directions. Notice that none of the forces, at least in this geometry, has any horizontal component. So I chose plus y to be up to be definite. It doesn't really matter which way plus x is because there's no x components in my problem that I'm giving here. So I'm going to do the sum of the force y components equals 0, and the sum of the torques about the elbow axis is 0. And I've just chose a positive direction. I chose counterclockwise, but it's no more difficult if you choose clockwise. Okay, let's first sum the forces. I've got 4 forces. It looks like we're presuming 3 of them are negative. You know, since we're solving for the elbow force, maybe you believe it's up, and we might find a minus sign if I guessed wrong. We've seen that before, right? But I'm going to sort of guess that it's in the direction downward. If I get a positive value for Fj, I think it is, the joint force, then then we'll know we guessed correctly. Okay, so 3 of them are negative, and only the muscle force, the biceps force, is positive in that case. Unfortunately, it's got 2 unknowns in it, both of those unknowns, so I'm just going to underline it, and hopefully I can get another equation from the net torque equals 0. And in this case, I guess it's called F mu. I can't read it on my scan here, but mu must be from the mass. I don't know. But in any case, or maybe that's an M. I don't know. The mass force, well, to calculate the torque, I'm going to do each of these forces times the corresponding moment arm. Since they're vertical, if I draw the line containing that force vector, the moment arm is the horizontal distance to the elbow joint. And notice that you're given all those horizontal distances. So that's great. We're kind of set up to do this way. Moment arm for the mass force, that's mg. Oh, I'm sorry, that's the muscle force. Okay, I see now. The muscle force has a moment arm of 5 centimeters. The forearm mass, I guess, is 2 kilograms, and it has a moment arm of 15 centimeters. And the 5 kilogram ball has a force of 5 times 9.8 at 35 centimeters. And in this case, notice the other unknown force was located at the joint. So that was one of the benefits of using that as the center of our axis of rotation, is that Fj doesn't appear in there. So I can just solve that for the muscle force and then substitute that into the equation above and get the joint force. And, you know, it's tempting to just say, boring numbers, but we might just sort of consider how hard the muscle has to pull up compared to how much the weight of the ball is. Now, you know, part of it is the forearm, but the mass of the ball is greater than the mass of the forearm. What's the weight of the ball approximately? It's a 5 kilogram ball, just very round numbers. How much does that weigh in newtons? 50 newtons, right? Because G is about 10 in SI units, right? So mg is about 50. Notice that the muscle force is 8 times as big about in this case. And that's pretty typical. When you hold a relatively small mass, you have to exert a huge force up, because to balance torques, my biceps muscle has a very short moment arm, whereas this smaller mass has a really big moment arm. Any questions on that last example that was on the worksheet? It's probably even easier than the last couple. You know, I think the diving board problem seems a little bit more confusing than this one. This is the last part to it where just it asks you to consider, well, suppose the forearm, same kind of model, same distances along the direction of the forearm, that it's dipped down at 45 degrees. How does the biceps force change in this configuration? And, you know, your intuition, you know, if you use those weight machines at the gym, maybe you realize they don't exert as much force when you go down like this. So maybe the biceps force is big when you're holding it horizontal, and becomes less and less and less, and it seems like it would become 0. Now, it depends on, you know, of course, it depends on the details of the model, but, you know, the only thing that really changed when I'm doing my torque equation, right? The torque equation told me directly what the biceps force was, that Fm. The only thing that changes, because the magnitude, the weights involved of all of these forces are going to be the same. Now, the joint force, we don't know that it's going to be the same, but who cares? When I'm summing torques, the joint force didn't come into it. The biceps muscle still has a 5 centimeter distance along the forearm, but it's not 5 centimeters of a moment arm anymore, right? The moment arms of all of these forces are reduced, right? Because when it was up here, the ball was sort of there, had a big moment arm, that full distance. Here, when I draw the line that contains that, it's cut down by a factor of cosine of 45. In fact, all 3 of the forces that come into the torque, the biceps muscle, the biceps force, the forearm force, and the ball force, their moment arms are all multiplied by the cosine of 45. Sorry, this is the force equation, which we're not really going to use here. But notice when I do the torque equation, I don't know why I did sine of 45. It really, at least in this picture, it seems like if you're thinking of moment arms, it would be the cosine of 45. Now, the cosine of 45 and the sine of 45 are the same number. But at least if I'm thinking in terms of moment arms, it seems to make sense to multiply by the cosine of 45. Maybe I was doing the F perpendicular times R, which might make more sense in terms of the signs. The amazing thing is, at least in this model, the signs all cancel out and you get exactly the same equation you had before after you cancel them all out. And so the claim is the biceps force. Now, that doesn't say that this model is totally how my arm is as I keep my upper arm vertical and lower down my lower arm like that. I experience when I'm holding something a little bit less force that I have to exert with my biceps muscle, but this is sort of a very approximate model. In this model, amazingly, the biceps muscle force doesn't change as you lower it down. Kind of interesting. Okay. Any more questions on that one before we go look at some homework problems? Yeah. Oh, actually, I think I have a voting question before that.
So why did you say that you would use cosine?
I would use cosine because I'm, at least when I look at this problem, I tend to think of moment arms. Let's see if this is in focus. Yeah. And so let's imagine that we're comparing, here's the ball force up here, right? It's 5 times 9.8 is the weight of the ball, just considering that one, right? And it was a certain distance. I think this was 35 centimeters out from the joint force, right? So that means that this distance here is 35 centimeters in the new way we're considering it. This is still 5 times 9.8. I'm just looking at just the part for the ball that was being held in the hand. And to find the moment arm, if I want to calculate this torque about this axis over here, and we're taking this to be positive, first of all, it's going to be a negative torque, right? So when I'm calculating my sum of the torques, this particular one's going to be negative because it's trying to twist it in the negative direction. And I'm going to use the formula F times R perpendicular, F times the moment arm. That's what I was thinking of when I was saying the cosine. Okay, and if this angle is labeled as 45 degrees, then the force magnitude is still the same. And the moment arm is given by, well, I always draw the line that contains the force vector and say, what is that perpendicular distance from that line to the axis of rotation? And so I would think of that perpendicular distance as 0.35 times the cosine of 45 would give this. 0.35 times the cosine of 45 degrees. It depends, if that angle is 45 degrees, well, of course, this angle is also 45 degrees. And, you could say, well, what about this side over here? Well, to get that, well, that's not going to be any different, but depending on which way you label that 45-degree angle, you might be tempted to put a sign in there. But does that explain to you what I'm saying, Abby?
Yeah, I'm looking at
Oh, yes. So if we want to think of it in terms of RF sine theta, what is that theta mean? And maybe that's what I was thinking of when I was doing this problem. Here's R. It's how far from the point at which the force is being applied to the axis of rotation. Here's F. And the sine of theta means always go along the R direction and past where F is being applied. And how far do you have to rotate over? Well, in this case, that angle is going to be 45 degrees because that angle is 45 degrees. Well, more because this angle is 45 degrees, right? That one's 45, so is this one, and so is this one. And so it doesn't matter because the sine of 45 is the cosine of 45. If it had been a different angle, right? If this angle had been 35, right? Then this angle would have been 55. And then it would matter whether I use the cosine or the sine. As long as I'm thinking about it the right way, either way, it doesn't matter which way you see it. But you got to remember the definition of what theta means. Go along R and tilt how far towards you get until you get there to the force vector. Other questions on that one? Oh, we're getting blurry again. Let me just stop and start the video. Okay. I think, as I said, I have a voting question here, which has to do with center of mass, which we haven't thought much about, but in some of the homework problems I wanted to discuss comes into it. Here's a box. It's rectangular cross section, and the center of mass might be in various locations, and the box in it is in a couple different orientations. And if the center of mass is where the dot is, in which of the cases, A, B, C, or D, and you can choose more than one, is the box going to tip over, or where will it be stable? Assuming it's not sliding, maybe the plane is grippy enough that it's not going to slide down the plane. But still, might it fall over in some of the cases? Help me think about that. What are we looking at there? Yes, Edward Lee. Right. I mean, it has to do with the fact that the plane, we're thinking of this box possibly being able to rotate about its lower left corner, right? And if the box is top heavy enough, it will sort of tip and rotate around that corner. Now, there are two things that can exert a force on the box about that lower corner. Gravity, which is, we're going to pretend is exerted at the center of mass, of course, can exert a torque about there. But the plane also can, right? If gravity is exerting a torque in this direction, the plane is happy to push back in that direction and counteract it and just keep it nice and stable by balancing the torque. If gravity pushes more in that direction, the plane just presumably pushes back harder. But what the plane can't do is pull back in that direction, right? If gravity is trying to tip it around in that direction, the plane has no mechanism to hold it back unless it's glued on the plane somehow. Presumably, it's just resting there. So the idea is in A, B, and D, gravity, by virtue of the force being applied at the center of mass that's labeled, is trying to twist it clockwise in A, B, and D. Gravity is trying to twist it to rotate in the clockwise direction, and the plane is happy to push back and cause it to rotate in the counterclockwise direction so that overall there's no net torque and it's just sitting there. Whereas in C, about this axis down there, the place that it might tip over from, in C, the gravitational force is exerting a torque that is causing it to want to rotate counterclockwise. And the plane has no mechanism to pull back on it and cause it to cancel by a clockwise torque. And therefore, in C is the only case where it would fall over. Any more discussion on that one? There may be something similar kind of in the homework. In any case, we'll see a couple of homework problems. Oh, you've got to be kidding me. I put some homework problems into my slides, and for some reason they're not showing up, but let me just open up a different version of this. I'm having problems with, I don't know if anybody uses OneDrive, but it's not always so good at synchronizing, but let me just pull up a different version of this and see if I can get those slides that I actually added with the homework problems on it. Otherwise, we'll just draw them at the board. Let's see, chapter 9. This is another one that I think I saved. Did I not? Oh, there we go. Let's just see. Yeah, here we go. Screen sharing is paused. That's a mistake. Let's see. There we go. Thanks. But I probably need to, I see. It's because I just shared my Microsoft stuff and sorry, technical difficulties, but here we go. Share screen, we want this one. Okay, here's a problem having to do with chapter 9. Something's in static equilibrium. Someone's got a ladder lean between floor and wall. Your numbers, of course, will be different in yours, but this is just my version of the numbers. And they're standing, you're given the weight of the ladder, which is at the center of, halfway along the ladder, 364 Newton ladder, and the weight of the person, 783 Newton. And we're given various distances on there. And the question is, calculate the force exerted by the wall. Now we got to read carefully here. Is placed, the first sentence says, a ladder whose weight is 364 newtons is placed against a smooth vertical wall. And smooth is supposed to be indicating that it's frictionless. Now, there are lots of things that are smooth and they don't behave in a frictionless manner. If you've got glass, it's nice and smooth, but if you put a rubber eraser next to it, there's lots of friction. So just because something's smooth doesn't mean there's no friction when you put something else against. But that's in these homework problems. If anybody says smooth, you can take that to mean frictionless. What that means is if this vertical wall is smooth, it means that the vertical wall can only exert a normal force, a horizontal force on the ladder. It can't exert a vertical force on the ladder because the vertical force would be associated with a friction force, right? Now the floor better not be smooth or this person's in trouble, right? If everything's smooth, the ladder is just going to slam to the ground. So the floor actually has friction, and you can think of there having to be two force components being applied to the ladder at the point where it meets the floor. You could think of a normal force from the floor, and then also a friction force, which pretty clearly has to be pushing to the right because it wants to kind of slide off to the left at the bottom. Okay, calculate the force exerted by the wall. Let's just do this together on the board, or you can help me set it up maybe. I don't have this as part of a worksheet, but let's think about it. I'll unshare the screen in just a second. First thing to do, of course, always is to draw just sort of a cartoon diagram. So let me draw the wall like that. Let's draw the ladder here. We'll draw the center of mass of the ladder. And I think I printed this out so I can just look at the numbers on here. The person is standing 4 meters up. So there's a force being applied here, which is, in my version, 783 newtons. And this distance is 4 meters from there to the bottom of the ladder. The ladder's mass, which is, we're going to pretend is being exerted all at the center of mass, 364 newtons. And that distance is half of 8.8. So we're told that the length of the ladder is 8.5 meters. And so presumably the center of mass is exactly at the center. You know, we're treating this as kind of a uniform rod. So that's 4.4, which doesn't look like the diagram I've drawn, but those are the numbers that are in here. Sometimes they have a range of numbers, and sometimes the diagrams look a little wacky because there's just one diagram for all the numbers. Okay, and so the question here is calculate the normal force. Let's draw the forces in that are being exerted on the ladder. We've got two of them here. Let me just switch colors to make it stand out. I might call this F wall. And then I've got one here. Clearly the floor has got to be pushing up on it. I'm not sure what to call that. Maybe F normal. We'll just know that the normal means the floor normal. And then there's also got to be a friction force. We'll call that F fric. And I think, so everybody agree, those 5 forces, given that the wall is frictionless, there's only one component there. There should be 2 separate components down there. And we want to know the force from the wall. There's no real rotation axis here, right? I could think of my rotation axis here, or the axis about which I'm going to sum torques and set them equal to 0, because it's in static equilibrium. I could do it here. I could do it here. I could do it down here. Anybody see a good reason to choose one over the other if we want the normal force for the wall? This is what's being asked for first. There's another part to this problem. Yes. Yeah, for the same reasons we just talked about with that beam that had the lever on it. If we choose our axis about which we compute torques to be down here, neither of these forces are going to contribute a non-zero torque about that axis because their moment arm is 0. So I'm going to take this point down here. That's my choice. I'm going to choose for it to be my axis. Why not choose positive clockwise? I don't have a good compelling reason to choose one way over the other, but just to be definite. And we're also going to be summing some forces, and let's put some axes on here. All the forces are horizontal or vertical, so let's take X horizontal to the right and Y vertical. And let's just dig in and see what we can get. We've got 3 things to go with. The sum of the force Y components equals 0, sum of the force X components equals 0, and the sum of the torques equals 0. Does anybody have an inclination as to which one of those might get us most quickly to solve for that wall force?
Would it be F friction?
Well, you're right. It's got to balance out F friction. So I think is that Nafiz who's jumping in there?
Yeah.
What you're saying is if the sum of the force X components equals 0, the wall force has to equal the friction force in magnitude, right? Because one has a positive, one has a negative component. They got to add to 0, and therefore they're equal in magnitude to each other. That's great, except that I want a number for the wall force, and I don't know anything about the friction force. So we found out the wall force magnitude is equal to the friction force magnitude, but I don't know anything about the friction force yet. I might be able to figure it out later on, but there's more work to be done there. Anybody see a way of those 3 equations that I talked about for equilibrium that could directly get us to the wall force with just one application of one of those equations? Yes. Yeah, the torque equation, because the 3 things I don't know are the wall force and the 2 that aren't going to contribute to the torque. So let's try the sum of the torques about that axis that I've chosen, and then we're going to set it equal to 0. So this gives 0. This gives 0. Here's a force, 783 newtons. What's the corresponding moment arm that I would, or how can I figure out the moment arm? I guess I've got some more work to do here. What do I need to know to figure out the moment arm for this weight of the person who's standing on the lower part of the ladder? Yeah. Yeah, if we were given an angle, say, for example, if you knew this angle, and I know this is getting kind of small for me to draw in there, but this angle here, I'm labeling as theta. If I knew that angle theta, then it seems like I know the hypotenuse is 4, and I would want 4 times the cosine of theta would be that moment arm. Is everybody okay with that? So now I'm going into a subroutine and think, how would I figure out theta? It's going to be the same theta that's relevant for the 364. You know, we've got a bunch of stuff to add into this equation. How could I figure out what theta is? Oh, I guess there's something I didn't write down in this problem. I forgot about that. 4.84 meters as I'm looking at it and realizing that I don't have enough information to solve it. This horizontal distance is 4.84 meters. Notice that if I rotated this, if I weren't given this number, of course, all the distances would stay the same. So there's no way to figure out what the angle is. It would be an ill-determined problem. But this horizontal distance from the corner to where the ladder is sitting on the ground is 4.84 meters. I just forgot to copy it from the diagram. All right, let me re-ask that question now. Is there any way to figure out what the angle theta is given that additional piece of information? Austin? Yeah, cosine. So Austin's thinking of this big right triangle here, right? Cosine of theta is adjacent over hypotenuse. And we know both the adjacent side length and the hypotenuse length, right? So let me just do a little side work here. Cosine of theta equals 4.84 over 8.8. Oh, luckily I brought my calculator. I didn't even think about it. We'll try to match the number. In my version, I can print them out with the numerical answers at the bottom. I'm hoping you guys can't do that. But for the instructor, it allows you to do that. So if I take the inverse cosine of 4.84 divided by 8.8, and since we've been using radians, I better at least check what mode I'm in. I'm still in degree mode. I get 56.63 degrees, just to keep 4 sig figs. Theta equals 56.63 degrees about. You guys on board with that? So tell me if there's something you're not understanding. So I'm doing force times moment arm. Here's the magnitude of the force. And its moment arm is going to be 4 times the cosine of that angle. 4 times the cosine of 56.63 degrees. And what else have I forgotten? Yeah, I've forgotten an SIGN sign, right? Because I've chosen this to be the positive direction. This force is trying to rotate it around in that direction. So it's a negative torque by my sign convention. Okay, that's one torque. This is exerting a torque, and this is exerting a torque, right? Negative, negative, and positive. So let's put those in. Minus 364 times 4.4 times the cosine of that same angle. And I'm about to run out of screen space, so I better move over here. Plus, this is going to be a positive torque, right? Because it's trying to twist it around in that direction. F wall, and in this case, maybe the easiest thing, well, I guess there's several ways I could do it. I could either figure out what the perpendicular component of the force is, right? if I knew an angle, let's see, this angle is theta, if this one is theta, right? And if I want the perpendicular component of that force, that would be F wall times the sine of theta, it looks like. Okay, F wall times the sine of theta, that's my F perpendicular, times the full R, if I'm doing it this way, times 8.8. And it's coming in with a plus sign. We could also do it in terms of the moment arms, right? I mean, I could say, draw the line that contains F wall, and we need to figure out what this distance is right there. That would be the moment arm for that force. And that would be 8.8 times the cosine of theta. Did I get something wrong here? This angle is theta, so that angle is theta. 8.8, oh, and I want 8.8 times the sine of theta. We want this side, yeah. 8.8 times the sine of theta. So you can think of that as your R perpendicular times the full force. Yeah.
So it's the 56.63 go in the parentheses?
Yeah, I just didn't want to keep writing the same number. I'll put a theta in there. Okay, and the sum of those three have to equal 0, and notice the only unknown is F wall, because the other two unknowns didn't go in there. Anybody calculate this already? No. 783 times 4 plus 364 times 4.4 all times the cosine of 56.63. Okay. And then I need to take that answer and divide by the sine of 56.63 and also divide by 8.8. I'm getting 354.3 about. Tell me if I've miscalculated anything, but I think I found F wall is, well, 354 point close. I must have rounded somewhere. I'm getting 354.28. They get 2.4, but you know, to 3 sig figs, it looks like we agree. Questions on that? The second part of this problem actually asks, I just didn't bother to put it on here. Calculate the normal force exerted by the floor on the ladder. I'm not going to do it, but you just tell me how you would start that. We want this force magnitude, which I've labeled as Fn. Yeah. Yeah.
Last part. Wouldn't the force of the wall be negative according to our axes?
The X component, so there's a difference here. You know, when I label things on a free body diagram, and I'm thinking of this as an extended free body diagram, either the symbols or the numbers I put next to them, if I know them, are always the length of a force vector, not a component. So you are right that if somebody said, what's the X component in this set of axes of the wall force? But I'm just saying F wall represents how long this vector is. 364 newtons is how long this vector is. Now, it would have a negative Y component, but that's the length of that vector. Good thing to remind us of. Okay, back to the question of what's the easiest way now if I wanted to most directly get that normal force? Which of my 3 equations would I go to? Some of the force Y components, X components, or torques? Well, some of the torques, we'd have to choose at least a different axis if we were going to, because we clearly didn't get it out of here. Some of the Y components, right? So 2 of them have 0 Y components, right? So that means this force is equal in magnitude to the sum of these 2 forces. So it's even easier than the one that was asked before that, right? All right, any more questions on that one? Okay, let's do something a little bit different then. Here is a person that has a scaffold kind of thing with two supports. We're given the plank length, we're given the mass of the plank, and there's 1.2 meters hanging over the end of the scaffold. That's L, I'm assuming. And then a certain person wants to walk on the overhanging part of the plank. How far do they get before it starts tipping over and the person is unhappy? I don't know how to do that here. Here's a meter stick, right? If someone starts going farther out here, at some point it's going to tip over. We all, I assume, have that intuition. All right, let's draw an extended free body diagram. You know, since there's several forces being exerted on the plank itself, it seems kind of irresistible to use the plank as the subject of all the forces that are being talked about here. Yeah, let me unshare this and I'll try to just draw a picture on the screen, on the board, I mean. And I'll put in my numbers. So we've got a plank. It's got some little supports that in the figure look kind of like this. The length of the plank is given in my version to be 8.9 meters from one end to the other. This is 1.2 meters overhanging that second support there, if I understand it correctly. The center of mass of the plank is right in the middle, and we're told that the mass of the plank is 40 kilograms. So that means the weight force here is 40 times 9.8. And of course, it's going to be half of 8.9 from one end, if you like. We could say 8.9 over 2 from there to there. That center of mass is supposed to be right in the middle of the plank. And what else do we know? There's a person of mass 330 kilograms who's standing over here. 330 times 9.8, that's their force that the gravity is sort of applying down via the normal force on them. And we want to know, what is this maximum distance x that they could walk beyond there? You know, if they're not too heavy, they could stand pretty close to there and it wouldn't flip over, but at some point, the whole thing's going to start flipping up. Anybody have an idea about how to solve this? Clearly, I hope you have the intuition that as this person walks back and forth, the forces being applied by these two supports here are going to change, right? If the person stands right over this one, this is going to exert a very big force up, right? As they start walking over here, more of the force shifts there, but some of it's still on there because the plank has its own weight in addition to the person walking, right? What special is going to happen when the person is just about to be at the point where it's going to tip over? On both of them? Sorry, I didn't hear that last part. Yes, the one over here, you know, you can imagine that if the person walks a little bit further, of course, this thing is lifted off. And so that force has gone to zero. And as the person walks back over here, the force gets bigger and bigger and bigger on this one. But this upward force on it is going to be zero if the person is at the point where it's just about to tip, right? Because if they walked a little bit further, it would actually have to go down. It's pushing up less, less, less as they walk out. At some point, this force is zero, and that means it's just sort of hovering. It's about, you know, it doesn't really push down on it anymore. And if they walk a tiny bit over, it starts tipping up, which would mean if it wanted to stay in equilibrium, this one would have to start pulling down. It doesn't have the ability to do that, presumably. Okay, so if I'm going to finish this up with forces in here, I better put in some forces. And I'm going to say for the case that I'm interested in, I'm interested in the case where that force goes to 0 newtons. It's in equilibrium, just barely, but there's a 0 Newton force there. There's some other force here. I don't know what to call that. F. I'm trying to draw all the forces that are on it, right? There are 2 downward forces, and then the only thing that can push up are those 2 that are there. And I can do the sum of the forces equals 0, horizontally and vertically. And I can do the sum of the torques equals 0, horizontally or vertically. Anybody have any intuition about, at least for summing torques, where I might want to choose as my axis to compute the torques relative to? Am I asked for F, the upward force from that second support? No. So there's an easy way to get rid of F, at least in the torque equation, and that's by putting my axis at the location where F is being applied, or at least so that it has a 0 moment arm. So in this case, I'm going to choose, because I don't want to know F, it's not going to come into my torque equation, and my hope is that, hey, maybe I can get X just from the torque equation. I don't have to bother with the sum of the force X and sum of the force Y. We'll see, but I like counterclockwise being positive, although there's no reason to be biased in that direction. But I'm going to choose counterclockwise to be the positive direction and this to be my axis. And let's just hope for it. Let's write the sum of the torques equals 0. Let's fill that in. 0 torque, because the force is 0, right? I'm writing down the case that I'm interested in. When this is 0 newtons, this is the X I'm interested in. That's the idea. So let's solve for X. Okay. First of all, positive torque or negative torque due to this weight of the board? It's going to be a positive torque, because notice it's on this side of that pivot. It's trying to twist it around there in that direction. Okay, so that one's going to come in with a plus sign. We have the magnitude of the force times its moment arm. Now, its moment arm isn't really shown on here. The moment arm for this force is this little distance. I know that's kind of microscopic on there, but I need that little distance there. And it has nothing to do with X, but can anybody see how to calculate it? Austin? Yes, so what has to add up to 8.9? Well, 8.9 over 2 plus 1.2 plus this little bit that I'm interested in there. So we'll just, maybe I'll call that D or something like that. I don't know. Let's do a little side calculation down here. 8.9 equals 8.9 over 2 plus 1.2 plus that D that's going to go in my moment arm, right? Anyone got that calculated? (8.9) over 2 minus 1.2. 3.25. Yeah, again, I'm getting fooled because my diagram looks a little bit wacky, but 3.25, you guys agree with that? D equals 3.25, so I'm going to multiply by this moment arm 3.25. No angles to get messed up with here because all the forces are vertical. Okay, positive torque again because it's trying to twist it in that direction about our chosen axis. Okay, how about this force, positive or negative torque? Negative. 330 times 9.8 times the unknown distance X. That's going to be our variable, right? And this one's 0 torque, And this one's zero torque because the force is zero, right? This one has zero momentum. So that's nice. Some of those two have to equal zero, and I can solve for that x. And let's say, oh, we can see my answer still, at least if you're in the classroom. We don't even need to put the 9.8s in there. 40 times 3.25 divided by 330. Whoops, what happened? Let's quit out of there. Somehow I type, oh. 40 times 3.25 divided by 330. 0.39393939. All right, that looks good. That's what my numbers are supposed to give. So that's another useful thing to think of. It's sort of like the box flipping over. You can think of as the center of mass of that box in the voting question we did moves higher and higher. You can think of there's less and less of a force from the plane pushing back. And at some point it goes to zero. And if the center of mass moves any higher, that would flop over. This is somewhat similar. Any more questions on this one before we move on to a last one? Oh boy, we have 1 minute left. Let's just look at it. Maybe we have enough time to talk about what to do on it. Here is, it's like my meter stick on the table. It's projected off by a certain distance, and someone wants to be able to walk to the end of this with their mass and just barely have it not tip over. In other words, they want to project it out as far as they can and still with their mass stand on the end and have it just barely not tip over, right? They want to be able to get out as far as they can. This is a huge thing, right? 15 meters there. So here the idea is, again, we have a potential tipping point in the middle, right, that we don't want to tip. And you can think of this whole side of the meter stick, or the plank in this case, generically is going to be pushing up in this direction. But when you get to the point where it's just about to tip, there's no upward force from the table on this part other than right at the edge, right? It's about to go to zero. So the only upward force is going to be from the edge. You're going to think of it as just hovering a little bit off the table, so it's only touching it at the edge. And we'll have the person's force at the end, the table's force there, and no other forces that are exerting torques about the possible rotation axis right there at that end. And of course, the person's force will involve an x, so hopefully you'll be able to solve that for an x. This, just seems a little bit dumbfounding to people a lot of times the first time they see it, but the principle is kind of the same as that scaffold thing we were just looking at.